Okay, so Massimo asked me on Friday if I wanted to talk about something, and then I asked him, so what should I talk about? And he said, whatever. So I will talk a little bit about the called PTA. So I guess most of you is familiar with this acronym here, all of you. Okay. So this stands for Pulsar timing array, and is one of the three, let's say, way that we have to measure gravitational waves. Four, yeah, come on, serious, seriously, hi cosmologist. So yeah, ground-based interferometers. In the future, we will have space-based interferometers. And at very low frequency, we can actually detect gravitational wave by monitoring these pulsars. Okay. So since probably most of you know a lot of stuff about gravitational waves, but probably many of you don't know much about timing of these pulsars, I will give a little bit of introduction to that. Since I don't know much about timing of this pulsar either, it's not going to be very technical. But the thing is very simple. So the basic idea of detecting gravitational wave in the second pulsar is to exploit the exquisite stability of the time of arrival of pulses on the second pulsars. So the second pulsars are spinning neutron stars. Okay, at the spin. That's tough because we have at least three different frequencies in this problem. So I will call these, how do we call it? No. Nu? No, alpha. Let's say nu. Okay. Nu is the spin frequency of the pulsar. Okay. So and this is, it's a huge spherical mass in vacuum. It has a huge moment of inertia. It's a very stable rotator. Okay. So when you time, this is there's some magnetic field, and it's some radiation, and if you are here, and you're in the, no wait, sorry. So, I really messed up the first row. So, that's a pulsar. It rotates like this, but it has some misaligned magnetic field. So it emits some radiation, and if you are in the direction of the radiation, this thing is spinning, is rotating, is a lighthouse, and you have pulses coming at you. Felipe, is it clear? They look like. So you measure basically the time, so you have your big radio telescope, and you measure these pulses. And if you have a time here, and you have some intensity flux or work of your radiation, you just work something like this. Okay? Very regular. Okay. So what you measure, so actually what you're measuring is a series, let's say for any purpose of time of arrival, T1, T2, T3, etc. Okay? Now, so what you want to do is to find in the series of this time of arrivals, basically the imprint of tiny variation induced by the passage of gravitational waves, and we'll see later what kind of variation we're talking about. Okay? So first of all, you have to model basically this time of arrival series with a timing model. Okay? So your pulsar is a clock. It has some period. Okay? The period of rotation. Then, because it has a big magnetic field, it's probably slowing down because of magnetic braking. Okay? So you have a dot. Right? And you have actually a p-double dot. Okay? Then your pulsar is somewhere in the sky. So you have, delta and right chance of declination, position of pulsar in the sky. It might well be in a binary, because millisecond pulsars are recycled pulsars, and many of them live in binaries. Okay? So if they're in binary, you have a series of parameters theta that defines the configuration of your binary, the period of the binary, etc., etc., etc. Now, you construct, let's put this, you construct a deterministic model that encapsulates all these variables, which are called theta and theta, okay? And then you say, okay, this model, and basically what you do, in fact, you have a function of all these parameters, and basically you match the time of arrivals that this function predicts to the time of arrival that you measure, okay? So if you are a good data analyst, you just take your supergroup Bayesian search in all the parameter space, and you basically find all the parameters here to match your time of arrival, okay? Of course, when you do that, if your observations are perfect and your model is complete, okay, then you do Ti predicted by your model minus Ti that you observe, and okay, and if everything is perfect in an ideal world, this is 0. Okay? So you have a model that describes exactly your time of arrivals. However, the world is not perfect. There are noise in your observations, and most of all, your model, you have no hope that your model is not complete. Okay? The pulsars are, we don't know anything of what happened inside pulsars, basically. And so there are sources of noise that probably you don't even know about. So your model is likely to be complete. Then, of course, your observation is not perfect. You have all sorts of noise, etc., etc. So this thing is not going to be 0, but it's going to be some thing that I will call residual. Okay? So if now I plot my residuals as a function of time, I'm going to have something. So this is each point here is basically, so this is time. So this is the first observation. Here, this is the second observation. So this is the number of observations, and here is what is left. And if I fit a function, here is something like that. Okay. Now, in here, basically, there is the noise due to your observations, and all the things that you don't know. Well, all the things that you didn't capture in your model. Okay. So this model here is a deterministic model. Okay, you have parameters that are determined precisely. Okay, it's not a stochastic. It's not a stochastic function. Okay, it's a deterministic model of n-pi. It's a function of some parameters. Okay. However, there is a bunch of things that happens in this system that determine this kind of behavior here, and I will tell you about a couple of them. So the first is the M variation, and this is a chromatic red noise. So the thing is that your pulsar, well, it's not in vacuum, and there's no vacuum between you and the pulsar. There is dense, not very dense, but there is a gas of electron, a free electron given by your interstellar medium. Okay, and basically the radio photons are scattered by this electron, and they take different paths to come to you. And in particular, low frequency photons are scattered more than high frequency photons. So that if you have now an observation, so this is a time of arrival, okay? And this is now, so the frequency of the pulsar was nu. This is, let's call it mu. Okay, mu is the frequency at which you observe with your detector, okay, of your radio telescope, which is not the rotational frequency of the pulsar, okay. Your pulsar will emit some radiation. Okay, will emit some spectrum of radiation, and with your radio telescope you observe, different band of this spectrum. Okay, so this mu is the frequency at which you observe your pulsar. This is the time of arrival, and if you look at your how this plot look like, that pulse looks something like this. Okay. And this is because the low frequency are scattered more by the interstellar medium and arrive later. And this is also why, for example, it's very difficult to find pulsars or millisecond pulsars in the center of the galaxy, because the interstellar medium there is denser, so this curve here is much more stretched. And when you search for pulsars in your radio surveys, you're looking for period. You follow your observation, you look for periodic signal. If your signal is broadened over a wide band, you lose the periodicity and you don't find the pulsars. Okay. Now, what you do then, so this thing is sum A of I times mu 3 minus 2. Okay. We know that this scatter from theoretical physics goes with the frequency of the photons to the minus 2 power, and this AI here is an amplitude that depends on your, which is going to be different in any of the observations, because the interstellar medium between you and the pulsar changes with time, right? Clamps and stuff like that. So this basically defined a series A1, A2, etc. Okay, of that have some behavior in time, and define another component, a component of chromatic, because it depends on the frequency that you observe, red noise, because it's generally a red noise function. Okay, it's something that goes, it's modulated over long periods. Okay, so now, so when you model, so you have this effect. So this is, DM is chromatic red noise. Then you have, of course, your pulsar does stuff that you don't know. Okay? And so what happens now, if I have my, so suppose I have my residuals. Let's go here. I just want to. Now, I subtracted my timing model, and I have some residuals that do something like this. Okay? And let's say this is like, hey, come on. 100 microseconds, the level of this thing. Now, I model this component, this chromatic component, and I subtract it. And I end up with something maybe like this. And this is now, this y-axis now is 10 microseconds. Okay? So you see here there is still stuff. Okay? And this stuff is whatever process happens in the pulsar that you don't understand. And you model it as an achromatic now, because it doesn't depend on frequency, red noise. Okay? And the way to distinguish between the dispersion measure, so the effect or propagation effect in the interstellar medium, between the intrinsic sources of red noise of the pulsar is exactly this, because one is chromatic, depends on your observation frequency, and the other one is achromatic, doesn't depend on your observation frequency. Okay, in principle.
Why? Why does it have to be achromatic?
Well, in general, that's the case. I mean, well, it's not exactly the case, in fact, because then what happens is that if you look at pulse profile at different frequency, you can find that there is profile shape evolution as a function of frequency. But in general, let's put it that way. Okay, this doesn't have to be necessarily achromatic, but in general, it doesn't have any dependence on frequency that looks like frequency to the minus 2 a priori. So, so whatever is left once you do this subtraction, in a sense, is some other red noise that depends from whatever the pulsar does. Okay, and the fact that it doesn't behave like this is what you use to separate. So I like to stress this point because that's exactly what you need to do here. You need to separate between different effects, because in fact, we will see in the second part of this talk that what the gravitational wave population of massive black hole binary does is to induce another red noise. Okay, and this one is achromatic. Okay. It has a power spectrum that we'll see in a second. so a specific power spectrum. But still, you know, it looks something like this in a pulsar. So if you just have a pulsar and you fit for your red noise here, you can absorb a lot of stuff that maybe are due to the gravitational wave pattern. Okay, and it's very hard to distinguish between the two. The way to distinguish between the two is to cross-correlate the signal in a family of millisecond pulsars, because this red noise is non-correlated between pulsars. Each pulsar does their own stuff, okay? And this noise has a very specific correlation between pairs of pulsars that you see in a second, okay? And that's the way you detect the gravitational waves with pulsar time. Okay, so you have in the end of the day, what you have is, so now I have to wait 5 minutes before okay, maybe. I just delete everything, so when I'm done over there, the first one is going to be dry.
While you're erasing, if we, no, go ahead.
Why you're erasing? I thought, why you're erasing?
No, that would be a very late question if that were my question. No, while you're doing this, let's suppose that somebody comes up with an amazing model of pulsars, which allows you to understand the pulse profile evolution from pulse to pulse, so that instead of having to average over hundreds of pulses, you can just do it pulse by pulse. Is this something, but there's still jitter or whatever else.
Right.
Is that something that would help a tremendous amount in detecting gravitational waves because of what you just said? Or are other noise sources dominant enough that this would be a mild perturbation on your accuracy?
Well, doing the analysis pulse by pulse, it shouldn't help you much in a sense, because so whatever changes happens on, you know, between one pulsar and the other, it's going to be whatever process happened in the pulsar that has an extremely low, extremely high frequency. Okay, and that's nothing that you have access to with your gravitational, so it's not going to affect the frequency range that you are probing with the gravitational wave. What helps you though is the following thing. Usually, when you construct these pulse profiles, you have you have a shape that is like this, and this shape is going to be different at different frequencies. Okay. So what people do, well, what people have done for a long, so if you have increasing frequency in this direction, so this is like this, well, this is something like that, and what people have done for a long time was just to use an average profile. Okay. Now what helps you a lot is to do two-dimensional profiles in frequency, in time and frequency, and that helps you take into account properly for all these changes, all this physics that affects basically the shape of this template as across the frequency range. But this is something that there are a couple of implementation of this kind of algorithms still ongoing work. Yeah.
Thanks.
Just a quick question. When you said that gravitational waves are achromatic red noise, I presume that means you're looking for stochastic background and not for an actual gravitational wave with...
Well, they are achromatic from the standpoint of your observations. Achromatic means achromatic with respect to the frequency at which your detector is observing. It's not the frequency of the wave itself.
But the red noise part of it would be, is that, I mean, I'm trying to figure out why it's noise and it wouldn't just be a very...
Well, yeah, okay. It can be...
Okay.
Okay, so, yes. So, so basically you have timing model, you have VM variation, you have some red noise, okay? So if you now take your time series, etc., do Fourier transform, etc., you get your power spectrum, okay. And your power spectrum of the noise is something that looks like, so this is the white noise, a Gaussian white noise component of your timing residual. Okay? There is radiometer noise in your observation, so every time of arrival you're gonna measure, it has some random fluctuation in it. Okay? So this is a white noise component, which in principle is what is left when you subtract your timing model, because your observations are noisy, if you don't have anything else here, if you don't have very noisy stuff. Then you have, like, you have a component which is SDM of F, then you have a component that is SRN of M, of F, okay, etc., etc. Okay, F now is the Fourier frequency, basically, the frequency when you do the Fourier transform in your time series. And this is also the frequency at which you are detecting the gravitational waves. Okay, so this is now our frequency for the rest of this presentation. Okay. Now, if you have a gravitational wave in here, you have something else. And how this something, what this something else look like? Okay, we're going to talk now. So the easiest thing is you have two massive black hole. Oh, first of all, what you're doing with this delta t here is the time between subsequent observations. Okay, so your pulsar timing experiment. In your pulsar timing experiment, you observe millisecond pulsars for several years, 10 years, 20 years, with a cadence of, let's say, weeks, typically. Okay, so by definition, in practice, the frequency at which you are sensitive with your experiment is basically of the order 1 over t to 1 over delta t. Well, in fact, 2 over delta t. No, 1 over 2 delta t is the Nyquist frequency. So this is 10 to the minus 9, let's say, and this is order 10 to the minus 6. So we are seeing, with pulsar timing array, we can prove very, very low frequency waves. It's much lower than advanced LIGO, it's even much lower, it's also much lower than the milliards regime that you proved with Lisa. Okay? The most prominent sources of gravitational wave at this frequency are supposedly massive black hole binaries. Okay? So massive black hole binaries are systems that are defined by basically two mass and a separation for any purpose, any other discussion, and they emit a gravitational wave h, okay, which is something that goes with an amplitude, okay, times the cosine of omega t. So omega is the
Angular frequency.
Angular frequency of your binary. Okay. Now, of course, now if you, well, I'm not going into the derivation or anything, but oh, maybe let's see. Let's see. What time is it?
It's 10:27. You got
Ooh,
plenty of time.
Okay, yeah, there's also plenty of stuff. So what happens basically is the following. So you have the pulsar here, you have the Earth there, okay, and you have a gravitational wave passing by, okay, and this gravitational wave is a distortion of the space metric. And so basically what it does, it makes the pulsar as seen from the Earth coming toward you and receding. Okay. So suppose that this is a wave that is propagating at the speed of light. At the same time, there is some part of that wave at the Earth that is hitting the Earth, that is making the Earth moving and receding from the pulsar. So basically what you see in the end is a Doppler shift. Okay? And it's a Doppler shift, so the effect of the passage of this gravitational wave on this puzzle, on that system, is a Doppler shift that I call delta Z for some reason, which is, this is the frequency of the pulsar, remember from the beginning. This is the intrinsic frequency of the pulsar, and this is basically equal to h at the pulsar minus h at the Earth. Okay, so at the moment, and in fact, this is the h at the Earth at the moment you are observing the pulsar, and this is the h at the pulsar at the time tau in the past, which is the travel light time between the pulsar and the Earth. Because when the pulse comes from the pulsar to the Earth, it keeps within the memory of the state of H when it was emitted by the pulsar. Okay, so that's the H at the light travel time before anything is coming. Okay, so but H has this, and the residual that this induces in your timing, in the timing of your pulsar, is basically the integral over the observation time of this delta z function in dt. Okay? And now, this is a cosine function, okay? So your residual is roughly something that is a over omega cosine omega t. And now we come to Matt's question. If I have an individual massive black hole binaries somewhere in the universe, and I look at the tiny residuals induced by that binary on my pulsars, it's going to be a sinusoid, okay? So here, in my system here, I have basically, well, some delta f, some stuff that depends on stuff. That is basically the frequency of my pulsar, okay? Now, orders of magnitude. For a massive black hole binary of 10 to the 9 solar masses emitting at a frequency of, let's say, 10 nanohertz. So if m is equal 10 to the 9 solar masses and f is of the order of omega is pi f. Pi not 2 because the gravitational wave is the second harmonic. F equal, let's say, 10 nanohertz, and put the distance to the pulsar of your massive black hole binary to, I don't know, let's say 100 megaparsec. Okay. This H is of the order of 10 to the minus 16, something like that. Okay. H over f, H over omega, it's H over f basically. So there is a 10 to the minus 8 here in Hertz. So your residuals is of the order of, let's say, 10 nanoseconds. Okay? So these are roughly the orders of magnitude we are talking here. In order to measure gravitational waves from a system that is realistic, okay, you need to be able to time these second pulsars with, several nanosecond precision. Okay. Well, in fact, you can take a system which is more at bit higher frequency, then this becomes 100 nanoseconds, let's say. But so 10 to 100 nanoseconds is ballpark. The time kind of accuracy that you need in order to be able to measure distance. This is good news because there is a bunch of millisecond pulsars that we can measure with the accuracy of, let's say, over 100 nanoseconds, over a time baseline of about 10 years or more. Okay? Good. So, all clear to now? Questions? Good. Now, I delete this hopefully for the last time. So this, however, what I just showed you is what happened for, maybe I keep this, what happens for an individual pulsar, right? But, luckily enough, well, we don't know really, hopefully, I should say, there is no individual, there's not only an individual supermassive black hole binary in the universe, but we're going to have a huge population. Well, this is right in the middle and it's very annoying, so I will just rewrite it. Okay, the thing is that as Francesco said a little bit on Friday, okay, So we observe massive black holes basically at the center of every galaxy, and these massive black holes come from some seeds that grew in time over cosmic history through a sequence of accretion mergers and accretion episodes. Okay. Well, I think we're pretty much confident that most of the growth of the mass of this black hole comes from accretion, in fact. But merging of galaxies is a very common thing in the universe, and we observe tons of galaxies merging everywhere. And if the host galaxy, a massive black hole in their center, this massive black hole is going to merge, hopefully, as well. Okay. And so what your signal coming from your Pulsar timing array is not going to be not going to have individual massive black hole binary emitting somewhere in the universe, but you're going to have a population of massive black hole binaries. Okay. Now the thing is, try to understand a little bit how this population looks like and how you're going to model it. Okay. And this is a quite simple thing, in fact. And let's see whether I can make this simple beyond all those scruples that I have here. So basically, the end point of all of this would be the following. The signal that you're going to see in your Pulsar timing array, you take a picture of the sky, right? You count how many binaries you see emitting at a given frequency in your detector, and you sum up in quadrature the amplitude of your signals. Okay, so this is basically it. Now, and this comes from a fairly long theory. I'm not sure I want to look into this. I feel with some mathematics or more physics.
Well, are you
Well,
talking about how to bias the quadrature?
I will just write this down, and so it can be shown very easily that basically the characteristic amplitude, which is some quantity that I haven't defined. Suppose you have now a signal which is not deterministic because it's an incoherent superposition of a number of sources that you don't know. Okay, so by any means this is a stochastic background. The amplitude of your background, the expectation value of the background, is 0. Okay, so if you want to play the trick you were doing before, oh look, you have H, you have the residuals, and you see the residual, doesn't work. This is 0. Okay. However, the variance of this thing, which is, let's say, H star of F, H of F prime, okay, is basically equal to delta F minus F prime SH of F. So what you can measure is the variance, okay? And if this is a stochastic, Gaussian stochastic corrective background, basically all the information in this is given by the power spectral density of your signal, okay? And for a stochastic gravitational wave background, this SH of F can be written as a constant characteristic amplitude of your signal at the frequency F divided by Ft. Okay? So, if you know the characteristic amplitude of your signal, okay, as a function of frequency, you have everything to determine the power spectral density of that signal, and you might remember from before that there was this series of power spectral density of stuff in there, and you can just add it to your experiment. Okay. Now, this SH of F, this HC square, if you have a population of massive black hole binaries, that is given by, it can be shown that is given by HC of F is equal to integrals 3n So, this is exactly the H that we saw before. H equal cosine omega, etc. And this is the differential number of sources in the universe emitting the given redshift with a given chirp mass in a given logarithmic frequency p. Okay? So if I take a picture of the sky and I know how many, and I count how many binary with a given chirp mass at a given redshift emit in a given frequency, and I sum up their amplitude square, this is the characteristic amplitude that I get. Okay? In the limit where you have many. Oh, yeah, sorry. Thanks. So this is the square. Since this is an incoherent process, you sum up the squares of the amplitudes. Now, in the limit of many sources, you can basically approximate this as a smooth function. And actually, I want to write this a little bit differently, which is by doing this. Here there are stuff like observed frequency, redshifted frequencies that are 1 plus z flying all over the places. We don't care about that. Okay. And when I write it like this, d dt in d logarithm of f. Okay, now this is, so this is useful because we can understand using this formula the shape, what are the physical ingredients that make the shape of this bed. Okay. Now, this is now something very useful in terms of computationally, because this is now the number of merger in the universe per unit redshift, unit chirp mass, unit time. And this is something that if you have a cosmological simulation or a merger tree or whatever, you can very easily count from your simulation. So this is an input that it's easy to understand, to get from whatever model you have. This tells you basically each merging binary how much time is spending emitting at a given frequency. Okay? So if I know that there is a merging binary per year in my universe, okay, then I know that at any given frequency there has to be that many binary in order to sustain the merger rate that I measure. Okay? Because this is a continuous process. So if binary is merging every year, so it means that there is a binary meeting at some frequency that is ready to merge the next year. And there are another binary meeting at another frequency that is ready to merge at 2 years. Okay, you could just say this is simply continuity equation. But anyway. So this is the merger rate, and this basically set the amplitude of your signal. So if you measure a gravitational wave signal in your constant timing data, the amplitude of that signal to some extent tells you something about the population of merging massive binaries in the universe. Now this part here, okay, because this H here is also a function of the masses, the redshift, etc. Okay, and the frequency. So this part here is basically what is the frequency drift of the it's the inverse in fact. What is the frequency drift of the binary? Okay, because of emission of gravitational waves. And we know that the F in the T, so the frequency drift of the binary is a function of time due to gravitational wave, is something that is proportional to the chirp mass to the 5/3 times the frequency to the 11/3. Okay? This is what we call chirp, because the F, the T increases with F. So it goes like, right? It's a chirp. And of course, more massive binaries shrink quicker because they have more mass, they are energy angular momentum. So now the F, the T goes with F to the minus 11/3. So the T in the log F, I would guess, would go like F to the minus 8/3, roughly. H, the amplitude of the gravitational wave, in a frequency is something that goes with, well, again, u to the 5/3, in fact, f to the 2/3. Okay? So, this times f square, h square is f to the minus 1/3 times f to the 4/3. So this is f to the minus 4/3. This is h square. So h, c, is some amplitude. I take some, frequency, reference frequency, which I measure this amplitude, to the minus 1/3. Okay? So, a stochastic gravitational wave background from a population of massive level binaries in the limit where we have many sources, so you don't care about the small number statistics, etc. These binaries, I assume that they are circular and that they are driven by gravitational waves, so the frequency drift has this functional shape here. Is a stochastic background, is a stochastic signal with the powers, with the HC, with the characteristic amplitude that goes with the frequency to the minus 2/3. This means that SH, this famous power spectral density, which is proportional to constants HC squared divided by Q, this is proportional. This is basically f to the minus 13. A stochastic background of gravitational waves produces a very, very red signal in your time of arrivals. Okay? So, if I now write the famous, the power spectral density of whatever is in your data, that's going to be some white noise component, then there is H S dm, then there is S red noise, and then there is this A f to the minus 13/3. And this is the power spectral density of your gravitational wave signal. Okay? Now, I want to say a couple of other things. I want to do with time.
Yeah,
I mean, you
15
can
minutes.
keep on talking unless
Ah, okay.
people
But we're not harsh on this.
Okay, good. Thanks. So, two things I want to say is, in practice, how are you going to detect this thing? Okay? Because this is a red process, this is a red process. Well, this is a chromatic red process of which you know that depends on the observed frequency. But it's very easy to basically exchange one for the other. Okay? And to see this, we will get to the concept of pulsar timing array and why it's important to observe many pulsars. And the other thing that I want to say, which is the first thing that I'm going to say, is that it's something about what happens to the spectrum when the approximation that I did, which are circular gravitational wave driven binaries, do not hold. Okay. And so I'm going to talk a little bit about this first part before, and this other thing before, because it gets me a little bit into. Is anybody talking about massive level binaries? Anybody else talking about massive level binaries?
No.
Okay, well. So it's an interesting point because, okay, we derive this thing, but we know already at the moment when we derive this that it has to break down at some point. Okay, because of course if you take a binary at a given frequency, it takes some time to merge, and if that frequency is too low, the time it takes to merge is longer than the other time. And so I'm going to draw here a very popular diagram, which is, this is binary, well, black hole separation of the two black holes. This is, let's say, 10 to the minus 3, 10 to the 3. These are parsecs.
Felipe introduced the proto array if you want to skip it.
Ah, okay.
You wish. Or just
Who introduced
Felipe.
Did you do those stuff? Okay, so you just have this, and gravitational, and this is the time to merge the binary. So the gravitational wave emission stage is something that goes like this, and this is a to the 4. Okay, so if you go beyond 10 to the minus 3, well, 10 to the minus 2 separation, basically this time becomes longer than the other time. Okay. So the thing is that depending on the masses of the binary and the frequency, etc., this thing happens pretty much at the lower frequency range, well, maybe a little bit lower than the lowermost frequency that you can probe with PTA. Okay, so you have to bring the binaries to this stage, so you need some process that is much faster than this, something that looks like that. Okay. And we know, because Felipe told us, that binaries go from kiloparsec down to parsec because of dynamical friction, and this is, well, it can also take more than ample time depending on the system, but for very massive equal mass galaxies, this is probably, a couple of giga years, okay? Then you get to some point where you form a bound binary, and you are at a separation of 1 parsec. And, well, if nothing else happened, that bound binary stays there for real time. End of story. 1 parsec, if you convert this in a frequency, is 10 to the minus 11, 10 to the minus 12, is well below the frequency range we could probe with pulsar timing. End of story, we go home, right? Which might be what happens. Yeah. Okay. So the thing is that these stars are going to be embedded in some environment. Felipe told you about gas, I guess, last week. I will tell, well, I won't tell really, but I will say a couple of things about stars, okay? So in particular, there would be a myriad of stars around this binary, and these stars some of them will intersect on the binary orbit, undergo a complex two-band interaction, and because they are poor light stars, they're going to be ejected from the binaries with a velocity which is much larger than sigma, which is the velocity dispersion of the stars in the bulge, and is of the order of the velocity with which the stars approach the binary. So basically, since they are ejected with much larger velocity, they take away energy and the binary shrinks. Okay? Now, if you do all the math and stuff that I'm not going to do, you find that this process causes a shrink of the binary, which is of the order of, well, there is this. Okay, so there is a number here, this is an adimensional number, but G is the gravitational constant, don't forget about this. Rho is the typical density of your stellar background. Okay, so how many stars you have per megaparsec cube? No, well actually this is how much mass you have per megaparsec cube. Sigma is the typical velocity dispersion of your stellar background. Okay, so if you take this and you translate it in, and you transform A in F, taking advantage of the incredible clever second law, you find that the F in the T is something that goes with F to the 1/3 now. Okay? So now we have a F in the T which is very different than this one that is coming from a gravitational wave emission. And in fact, well, okay, there are two things. So if I now transform this into a residence time like I have here, this goes with that to the -1, okay? And this df in the t goes with that to the 1/3 instead of that to the 11/3. So the thing is that these two mechanisms will cross at some frequency. Well, here it's some separation, but let's say the frequency at some frequency. So at low frequency, binaries will be driven by the interaction with stars, and the df in the t will be given by this scaling. At higher frequency, binaries will be driven by gravitational waves, and the df in the t will be given by this other scaling. Now, if you want, and we know that in the second case, hc is this. In this case, it turns out, if it's easy, you just have to put this df in the t instead of the other in there. You found that hc is proportional to, well, it goes with f. Okay? So, if you have a binary that is driven by some stellar by the interaction of stellar, if your population of massive black hole binary, the cosmic population of massive black hole binaries is driven by interaction with stars, and you want to find out what the characteristic amplitude is, I guess I will wait. Also. We there yet? That's okay. Now I plot frequency. This is a log scale. Okay, that's 10 to the minus 9, 10 to the minus 8, 10 to the minus 7. This is HC. This is also log scale. We don't care about it. Well, okay.